Hello everyone. So we have been discussing about different hazards related to pipeline. We have seen the different data hazards. We have discussed about structural hazards, and we are currently talking about the control hazards. Now, where from control hazard is coming? So control hazard, as we understood, is occurring because of the change in sequence of instruction, the way the instructions gets executed. For example, if when we are fetching some instruction, we are not we have no way to know whether it's a branch instruction or not. So we have seen in the last discussion that if we do not want to do anything without knowing, or for example, if I am not quite sure where the next instruction is coming from, and I wait till I become sure about where the next instruction is coming from, then we saw that the pipeline efficiency will significantly go down, because we can only know about the outcome, or only know about whether there is a branch instruction or not, at least at the decode stage, and then the branch outcome many a times will be available at the execution stage. So if we wait till that period of time, then we will not be able to push a new instruction in every clock cycle, and that decreases our efficiency significantly, pipeline efficiency. Now, to avoid that, what is the way out? The way out is that we do some speculation. Now, what is the speculation? The speculation is that by default there will not be any branch instruction, and we will go ahead and fetch the next instruction from PC plus 4. And with this assumption, we will go ahead, and whenever there is a branch instruction, we realize that we have whatever we have speculatively brought into the pipeline that was not supposed to be brought in, we have to get rid of those instructions which are not supposed to be there. So that we have seen briefly in the last discussion. So we will go back and continue our discussion from there. So just to pictorially show what I meant when we said that okay, we will not do any kind of speculation. So we have to wait till at least decode stage to figure out that okay, this is not a branch instruction, and then the next instruction can be brought in from PC plus 4, and so on. So if you keep on doing it like this, then you will see that your CPI will become at least 2. Okay, basically your CPI becomes double than what you could actually achieve with every instruction or a new instruction pushing into the pipeline in every cycle. So to avoid that, we speculate that the next instruction will be at PC plus instruction will be need to be fetched from PC plus 4, and we with this speculation we execute or we push things in the pipeline. So we looked into this example. So let's say these are the different addresses for each of the instructions. So there is an add instruction, so we fetch, decode, execute, multiply, and write back. Then we don't know what is this instruction at this point. So this is a, let's say, a jump or branch instruction. So depending on which ISA you are looking at, so basically it can be a branch instruction, branch to this location. Okay, so don't worry about the syntax, etc. And then we basically fetch, decode, and when we basically execute it, we realize that okay, this is a jump instruction, and the next instruction we need to fetch in is from this location. Okay, not from 104, which is PC plus 4. But by that time we have already fetched PC plus 4. We have fetched this instruction. So what we will do now, we have to kill this instruction. See, this is very important to realize that we can't just stall this instruction. Stalling means what? Stalling means like you wait for some time, and then eventually this instruction will get executed. But this instruction is not at all supposed to get executed, because after this instruction you are supposed to jump to here in this new location. So you have to kill this instruction. Now how do you execute this kill instruction? So there can be different ways. So one very simple way can be, in our simple RISC, one possibility can be you designate a bit which is kind of there to convert an instruction into no op. So if you set that bit, then basically you consider that instruction is no longer a valid instruction and it has been replaced with a no op. So that can be one approach. The other approach can be whenever the instruction moves from one stage to another, you pass it through a multiplexer, and one of the input to that multiplexer is a no op, and the select line of that multiplexer is triggered by this branch instruction. So basically whenever there is a branch, whatever you have speculatively brought in, there you replace the instruction with a no op, and that is how you kill that instruction. Okay. So so as soon as you realize that the new location from where you have to fetch the instruction from, you update your PC and you start fetching your subsequent instruction from here. Now this instruction which had to be killed, that also impacts your performance, because you did something which which didn't give you some outcome. So that reduces your performance, your CPI increases, and so on. All right. So this is called control hazard. Okay. So I hope this makes sense. Okay. So for consistency, let's instead of saying it as jump, let me just change it to branch, which is more consistent with our simple RISC instruction set. Okay, so we can look at one more example, and okay, one thing to highlight here is that since it was a unconditional branch, so you could decode at the decode stage itself. You can figure out that okay, this is a branch instruction, and by that time you reach the execution stage, you know that you have to kill the subsequent basically you have to start fetching the instruction from a next instruction from a new location, and you start killing the instruction here. But if it was a conditional branch, then the outcome of the branch will be known after the execution unit only, and by that time you will be fetching one more instruction, and so you have to kill two instructions. So I will just give you one example to highlight this point. So let us say we have another code snippet which looks like this. So this is the address, and here we have add, then in 100 we have branch if equal to 0, okay, and so basically if so let us say this indicates to a level which is offset by 100 units, so or 200 units. So let us say I am just writing it down as plus 200. So that means the address where it needs to jump to is PC plus 200, okay, the next PC plus 200. So similarly you have the other instructions like add, there is one more instruction here, any instruction, let us say subtract or something, does not matter, and then finally you have an instruction in this location which is, let us say, PC plus 4 plus 200, so it will be 304, and there you have a new instruction add. Now if you write down the pipeline diagram for this machine, for this code snippet, so we have let us say cycle number 0, 1, 2, 3, 4, 5, 6 and so on. So here we will fetch, decode, execute, memory and write back. Alright, so then we will fetch, decode. Now in this decode stage we know that okay, if we can read the opcode and we can figure out that it's a branch if equal, but remember that the outcome, whether the branch is basically the flag is equal to 0 or not, that will be determined by at the execution stage only, right? And then you have memory and write back. Now by the time you you figure out in the execution stage, you have already fetched this instruction. You will be even reaching at the decode stage for this instruction, and the next instruction, which is in location 108, that also will be fetched. So after this stage you will realize that okay, let us say the branch is taken. Now if the branch is taken, then you have to basically kill this instruction and you have to kill this instruction. So you have to replace it with no op, similarly this also has to be replaced with no, right? So next instruction will be fetched from this location 304. So then it will go into fetch, decode, execute, memory and write back. Alright. Now you see that two instructions needed to be killed because they were speculatively fetched, and we realized later on that we were not supposed to fetch them and not supposed to decode and execute them. That is why they were killed. Now if you look at the penalty of this branch instruction, so this penalty for this branch instruction is basically 2 instructions for this particular case, because your pipeline is 5-stage pipeline, and by the time you execute you can only fetch or you can speculatively bring in 2 more instructions. But think about a situation where your pipeline depth is more. So instead of 5 stage, it's a 10-stage pipeline. I can design a processor with 10-stage pipelines, and as I mentioned earlier also, like some of the Intel processors have very deep pipelines like 44 stages pipeline in Intel Pentium 3 or Pentium 4. Now think about it, if there are deep pipelines and the number of stages are much more by the time or basically before execution there are, let us say, 10 stages, then by the time you reach execution you have already fetched in much more instruction, and all those instructions need to be killed. So in that case the branch penalty, so basically the amount of instruction that you need to you have unnecessarily or speculatively brought in which need to be killed results in branch penalty, because it reduces your performance, right? So how do you address that? So to reduce the branch penalty there can be different strategies. So possible strategies can be okay, let me write it down. reducing branch penalty. So one very intuitive approach could be that can we instead of waiting for the execution stage, can we decode this thing, or can we know the branch outcome in the decode stage itself? So if we can do that, then we can reduce the branch penalty from 2 instructions to 1 instruction, because by the time the decode is happening, we will know the branch outcome. All right. So by the time if we can do something in the decode stage additionally to figure out the branch outcome, then the penalty in this case can be reduced to 1 instruction. How can we do that? We can do that by introducing some extra hardware in the basically decode stage. So if we look at the decode stage, so here basically we are saying that okay, we will be knowing about, so okay, branch part is not shown here, so this diagram will not be very helpful. So you need to have access to the basically the flags, and then you can compare. You need to have a comparator in the decode stage to compare the flag content and with 0, and if that is true, then you can figure out what will be the branch outcome. But as you can understand, that will add additional hardware in the decode stage, and it might even slow down the decode stage to some extent, and that as a result your cycle time will increase. So these are few things which you need to be aware of. The other more popular approach for reducing branch penalty is basically something called branch delay slots. Okay. So this is nothing but you are exposing the control hazard to software. What do I mean by that? For example, when the compiler or the programmer is writing this instruction, he knows that this branch will be taken, or let's say in at least for many of the cases the branch outcome will be known. If it is not a very conditional thing where the variables are changing, so in those except those situations, the outcome of the branch will be known to the programmer. So if the programmer knows that this branch will be taken, or if at the compiler level it is known the outcome of the branch, then what you can do, you can put some instruction in these slots which are independent of the branch outcome. So what basically it says that you figure out instructions which anyway will be executed whether the branch is taken or not. So what is the advantage? If I select if I can find out 2 instructions which are independent of the branch outcome and place them here, then I don't have to kill these instructions, because whether the branch outcome is taken or not taken, these 2 instructions will be anyway was supposed to get executed. So by the time I realize that okay, this is a branch, I will go to this new location, but these instructions I don't have to kill because they were independent of the branch outcome, and compiler has already ensured that, and that's why these 2 instructions will anyway get executed. Now here it's very very important that if I in my design, in my processor, if I use branch delay slots, then the compiler is aware that okay, I have to put 2 instructions, or depending on how many delay slots you have, let's say there are 2 delay slots in this example, depending so basically the compiler will figure out two independent instructions and it will put these two independent instructions immediately after the branch instruction. Now at the hardware level you will not do anything, because you know that compiler has already taken care of it, and whatever the subsequent instructions are there, they were anyway supposed to get executed. Okay. So just to summarize this, how do you exploit the branch delay slot? You expose control hazard to software. Okay. So in this process you will say that okay, the instruction that will be following a branch or a jump instruction is always executed. The instruction that follows a branch is always executed. Okay. So basically you are giving the compiler the flexibility to put a useful instruction where normally a pipeline bubble would have been resulted. So if this was not given, then I would have fetched something which I would have ultimately kill, and that I will be avoiding by giving the flexibility to the compiler to put in a useful instructions, to put in useful instruction after the branch instruction. Now depending on your design, you can select like how many delay slots you want to have. Most of the cases you will see that there are one or two delay slots in most implementations, because it's very difficult to find independent instructions beyond that. Okay. Because think about it, in your program there may be lot of branch instruction, and every time you have encounter a branch instruction, you have to find an independent instruction if you have only one delay slot, and you have to put that in that delay slot. And if you have two delay slots, then you have to find two independent instructions. And at the compiler level, if you do not find an independent instruction, then at the compiler level you have to insert no op here. Okay. So that basically is very important to understand that if you don't find an useful instruction, you have to replace it with no op, and no op is not going to help you in achieving any better performance. Okay. So just to put it in words, basically this gives compiler the flexibility to put useful instruction where otherwise this pipeline bubble would have been resolved. All right. So basically if we look at this example, the one we have looked at so far just now. So in this case we can say that okay, if I have one delay slot, then I'll put one instruction which is useful, and if I have two delay slots, then I'll put two instructions which are useful. Okay. And these instructions are executed regardless of the branch outcome. Okay. So, this is one of the techniques which is very widely used, but as I was mentioning, like some of the processors have very deep pipeline, but even like it will not be possible to find so many uh, instructions for if you have a deeper if you have more number of delay slots, because finding that many independent instruction is almost impossible. The other thing which we will not have time to discuss related to this branch control hazard is that how modern processor handle this branch penalty. So, all the modern processor has a very sophisticated branch prediction unit. So, the branches are predicted with 99.99 accuracy. So, most of the cases the compiler knows what will be the branch outcome, and that is why the sequence of instruction that need to be executed is pretty much known, and that way basically the control hazard or control hazard related penalty is reduced. Okay. So, basically advanced branch prediction techniques, um, um, uh, can dramatically reduce the branch penalty. Alright, so this is how you handle the control hazards, and like if you draw the modified pipeline diagram for a processor which has a branch delay slot. So let us say you can decode the branch outcome after this decode stage. So, if I have one delay slot, I will put a useful instruction here, and that way my CPI will be maintained, or CPI will be not getting affected very badly. Okay. All right. So now let us talk about very briefly, or to summarize, why our CPI will be most likely greater than 1, or why we can't why an instruction may not be dispatched every cycle. So, if we can dispatch one instruction every cycle, then we will have a CPI of 1. So, why an instruction may not be dispatched every cycle. So, basically why we will end up with CPI greater than 1. So, we saw that there are different kind of hazards. So, if we ignore the structural hazard, which we say that we can handle it by putting enough resources, like with non-unified data and instruction memory, we can handle that structural hazard. But then there are data hazard, and data hazard especially related to read after write kind of hazard. These are very these we can't ignore. So, we have to wait for the data, and then only we will be able to proceed. Now, one way to handle that is bypassing, right. We said that okay, instead of waiting till the write back stage, as soon as the result is available, we will try to bypass or forward it to the next stage, or basically to the previous next instruction, so that they can use the result. So, this is fine, but if you want to do this for every stage of your pipeline, or which in other words means fully bypassing, that can be very very expensive. So so if you truly want to have results from every stage available to the next instruction in the previous stage, then you need full bypassing, and full bypassing can be very very expensive, because you are, think about it, you are bypassing 32-bit data. So it's a huge bus running backwards, and your mux which is selecting between so the one new input to the mux comes which is 32-bit, so that increases the overhead significantly. So basically full bypassing may be too expensive, too expensive to implement. Okay. um, so how do you handle that? So typically you try to bypass very frequently used paths, and sometimes you also use some infrequently used bypass paths, but that can result in increased cycle time, and in a way can counteract to the benefit of reducing CPI. So typically all frequently used paths are provided with bypassing. The not so frequently used paths can result in overhead. Okay. Then there are conditional branches. Okay, before that we have not gone into the details very much, but the load store instructions also, especially the load instruction, most of the processor it cannot be executed in one cycle. So so if you are loading some data, you will not be able to use it immediately after load, so you have to wait for some time. So there are concepts like load delay slot as well, so that you do not try to use the data which you have just loaded. But yeah, we have not talked about it, but intuitively you can remember that the load result will be also not available immediately, because you need to read the memory, and once the memory is read, then only you can have the data, and that takes time. Now then there are other control hazards related to conditional branches. So there are conditional branches which are very difficult to predict, and in case of conditional branches, then you have to basically kill all the speculated instructions. So conditional branches can cause bubbles as well. Okay. So the way to so basically the branches which can be predicted easily, or for reducing the control hazard, you can use the delay slots, and these delay slots are you basically can reduce your branch penalty, but finding useful instructions are also very difficult, and if you do not find useful instruction, you will be the compiler will be replacing them with no op, and that in fact does not help in your performance. So so because of these different hazards, we see that though ideally we want our pipeline to look like this. So basically we in every clock cycles we will be you will be pushing a new instruction in the pipeline, but we see that because of all these challenges, all these hazards, it very likely that there will be some bubbles, and that bubble will in a way reduce our CPI. So just to make sure that you guys can visualize it properly. So if every clock cycle we can push a new instruction, so if I am sitting here, I can see that every clock cycle one instruction is getting executed. But if there is a bubble in between, then this execution time becomes longer, and as a result your CPI becomes higher and higher. All right. So right now if you look at it, like in 4 clock cycles we could execute 4 instruction, but if there was a bubble, then let's say I'll need maybe 5 clock cycles to execute 4 instructions, and so on. So as you have bubble in your pipelines, then it increases your CPI. So because of all these reasons, the CPI can be pretty high compared to basically our ideal CPI, which is 1. And to achieve this CPI of 1, the processors are modified to basically the hardware implementations are modified so that we have superscalar processor, we have which can basically sustain a CPI of 1 or less than 1. So what do you do there? You have multiple pipelines, you allow out of order execution, you also allow many other you put lot more resources to achieve higher and higher performance. So for example, very sophisticated branch prediction algorithms are used, and so on. A few things which we have not discussed related to control hazards are basically exceptions. So what happens when you have some exceptions like divided by 0 or memory fault, etc. So then also you will change your execution sequence. So basically exception handling routines are called, and your PC will change, and so on. So that needs to be handled, and that will result in basically penalty, because whatever you have speculatively fetched in, all these things can need to be killed. Similarly, along with exceptions, there are basically interrupts that also create this kind of control hazards. Okay. So this pretty much brings to an end to our discussion on pipelining and the hazards related to it. So I hope you guys could get an overview of all the things which we have discussed. So we talked about why pipeline is useful. So we motivated ourselves using different examples. So we had the analogy where we talked about the mess situation, where you go one after another to take food, and then we also looked into the car assembly analogy, and from there we started looking into the hardware pipeline. So we first look into how the processor without pipeline looks like, can be designed, and then how we can introduce this sequencing elements to break the whole execution into 5 different stages, and then using pipeline how we can execute multiple instructions simultaneously in different stages of the pipeline. So the pipeline gives us lot of advantage in terms of very good CPI, and also the length of, or basically the time period of the clock is minimal in a pipeline case. But we also in our discussion figured out that the pipeline which we implement is not as straightforward as the pipelines in, let's say, car assembly line or many other physical assembly physical pipelines. um, so the to deal with it, or basically there are different kind of hazards because of this dependency of instructions, etc. So we have structural hazard, which is basically different instructions trying to use the same resource at different stages of the pipeline, that can lead to structural hazard. So we can avoid structural hazard by appropriate resource allocation. And the other hazards are data hazards. So we saw different kind of data hazards, like read after write, write after write, then read after write, kind of basically write after read kind of hazards, etc. And we also saw that read after write kind of hazards are more critical for our in order processors, and we saw how we can basically address, or how we can minimize those hazards. So we saw that we can use bypassing for minimizing the hazard, and for correctness we can introduce stall logic, so that whenever there is a dependency, that dependency can be detected at the hardware level, and accordingly the instructions are stalled so that they can executed appropriately. Then we finally looked into the conditional basically control hazards, and conditional basically the different kind of branch instructions causes this conditional control hazard. To again so if you have a you have some branch instruction and you have speculatively fetch instructions which were not supposed to be executed, so you need to kill them, so that is called branch penalty. So the control hazard can be minimized, or the branch penalty can be minimized by having techniques like branch delay slots, where you basically immediately after branch you put an instruction which anyway was supposed to be executed, and that is done by the compiler itself. And if the compiler could not find out an instruction which is independent of the branch outcome, then it will put a no op there, so that the hardware does not have to do anything. Hardware will just execute or fetch the subsequent instruction without worrying about the branch outcome, and it will execute that thing. So if there is a useful instruction, that will get executed, and that way your CPI will not get affected. And finally we saw that though all these techniques are there, they have their limitations. So basically the full bypassing to solve the problem of RAW hazards is not very feasible, because that introduces lot of overhead, and the cycle time also can get affected because of all the overhead. The delay slots are a nice idea, but finding independent instruction from the branch is very difficult. Beyond one or two branch delay slots, it's very impractical to have more number of branch delay slots. And another way of basically minimizing the branch penalty is having very sophisticated branch prediction algorithms, and the state of the art branch prediction algorithms are pretty accurate. We can achieve up to 99 or even more than 99% accuracy in branch prediction, and that way you can minimize the control hazards related to branch. Okay, so that concludes our discussion on processor design, and subsequently we will move now to the memory part of it. All right, thank you.